So chemical formulas. So compounds have a specific ratio of atoms of each element, and the chemical formula is a shorthand notation of indicating what that ratio is. So it gives us the elements present in the compound and the relative numbers of each atom. So we use subscripts to tell us how many atoms of each element there are. So here's the formula for water, H2O. So this symbol H says there's hydrogen in it. The subscript 2 says there's 2 hydrogen atoms. Here's the symbol for oxygen, and there's no subscript there. This is another example of chemists not writing the number 1. So we could write the number 1 there, but do we really need to write the number 1? No. If it was 2 or 3, we'd write that number, right? If it was 0, we wouldn't write oxygen at all. So we don't really need to write the 1. This is like the old couple that have been married for a gazillion years. And she's like, "You never tell me you love me anymore." Well, I told you when we got married, and I'll let you know if it changes, right? So that's kind of how this is. So H2O, 2 hydrogens, 1 oxygen. So this is the chemical symbol or formula for table salt. Sodium and chlorine, 1 of each. 1 sodium atom for every 1 chlorine atom. Okay, 1-to-1 ratio. This ratio of numbers of atoms is not the same as the mass ratio. Because how much does a sodium atom weigh on average? Periodic table. What's the number under sodium? It's about 22.99, right? So a sodium atom weighs about 22.99 atomic mass units, and how much does the average chlorine atom weigh? 35.45. So the ratio of masses would be different than the ratio of numbers of atoms. CO2 is the symbol for carbon dioxide. There's no subscript after the carbon, so we understand there's 1 carbon, and O2 tells us there's 2 oxygens. So we have a 1-to-2 ratio of carbon to oxygen atoms. This is the symbol, the formula for table sugar, sucrose, C12, H22O11. So this ratio is a little more complicated. 12 carbons for every 22 hydrogens and 11 oxygens. Some of the numbers in these formulas can get pretty large. They're always going to be whole numbers, though. Because could you have 1.5 oxygen atoms? No. Because the atom is the smallest unit of matter. So it's a little bit like, saying average family size has 2.1 children. Does anybody actually have 2.1 children? No, you can have 2 children or you can have 3 children, but you can't have part of a child. This doesn't work that way. You can't have part of an atom. It's like, how many pencils? I got 3 pencils. You can't have 3.5 pencils. It's a pencil or it's not a pencil. So the subscripts are part of the compound's definition. If you change the subscripts, now you're describing either something that doesn't exist or at best a different compound. So there are 2 very similar looking formulas, CO and CO2, and let's not get this mixed up with the symbol for the element cobalt, which is capital C, lowercase o. CO is carbon monoxide. This is an air pollutant, and if you're breathing too much of this, it can kill you. CO2 is carbon dioxide. The difference is this one has 2 oxygens for every 1 carbon. That's a 1-to-1 ratio. This one's relatively harmless. There is a fair amount of CO2 in the air that we're breathing. We take in oxygen, we exhale carbon dioxide. It's not harmful in reasonable quantities. The only time it could be harmful is if you only have CO2 to breathe without any oxygen, then you'd suffocate, but that's true of anything that deprives you of oxygen. Carbon monoxide will be hazardous to you even at relatively small levels. Any questions? So the chemical formulas are always written in the same way, and it can seem a bit of a mystery. Because how do you know which element goes first? Why is it H2O and not OH2? It's a reasonable question. Well, we have a kind of a pattern. We'll see some exceptions to this because we don't want to go into all the details. But the general idea is the more metallic element is listed first, and then the less metallic. So in the examples here, NaCl, sodium is a metal. We can tell from the periodic table because it's on the left side of the periodic table. And chlorine is a nonmetal. So we're going to put sodium first and then chlorine. And it's just a convention that we have established. It's like when you address formal invitations to a big party or a wedding. Do you write Mr. and Mrs. or Mrs. and Mr.? It's always Mr. and Mrs., right? Why? It's convention. It has no significance on the relative worth of the people in the marriage, okay? It's just convention. It makes things easier and more consistent. So I think of metals as being masculine and nonmetals as being feminine. So we're going to put the masculine one first, the Mr. first, and then the Mrs. So there we have a metal and a nonmetal. Here we have nitrogen and oxygen. Well, those are both nonmetals. Well, look at the periodic table. Which one is closer to the metal side of the periodic table? Nitrogen. So let's put nitrogen first. Okay, so we'll put nitrogen first and then oxygen instead of the other way around. Would I understand what you meant if you wrote it this way? Yeah, but it looks pretty silly to me. It reminds me of when I was at a restaurant with my second child when he was about 2. And he pointed over to the receptionist, the hostess station, and she had a cash register. And he was going on and on about the dollar biller. I'm like, the dollar biller? And then I finally figured out he was calling a cash register a dollar biller. This was a thing that had dollar bills in it. I'm like, well, that's pretty creative. I figured out what he meant. Is this silly? Yeah, it's silly, and it makes a great story later. But this looks like dollar biller to me, when what you really mean is cash register. Okay? This is the specific order. I'm not going to hold you to that, but if you want to, if you're doing something in a homework or something and you need to look it up, it's there in Table 5.1 in your textbook. There are some historical exceptions. The one we'll see the most is hydroxide ion. According to the rules, we should put hydrogen first and then oxygen, but we don't. And it's just a historical thing. So let's write chemical formulas. So we have these guidelines for what order to put them in, but what you'll find in the homework problems and in exam questions and even in the worksheets and experiments, the elements are generally listed in the problem in the correct order. So if you just go with the order that they give them to you, usually that's correct. So let's write some chemical formulas. So a compound that contains 2 silver atoms to every sulfur atom. Anybody know what the symbol for silver is? Ag. So silver, Ag, and 2 silver atoms, I'm going to put a subscript 2 after that. And then sulfur is S, and there's 1 sulfur atom, and so I don't write anything. So Ag2S. What's this? That's what the Lone Ranger says to his horse. Hi-yo, silver. No? Do you know who the Lone Ranger is? Okay. Still wasn't funny. It's okay. The YouTube people think I'm funny. Anyway. Okay, compound containing 2 nitrogen atoms for every oxygen atom. Well, the symbol for nitrogen, N, there's 2 of them, and there's 1 oxygen atom, so we write capital O. I understand that some of you have atrocious handwriting. Some of my children have atrocious handwriting. It's okay. But for chemical symbols, take your time and form your letters correctly and get the sizes right. And then go back to your sloppiness, that's fine. But just for the element symbols, please. So compound containing 2 iron atoms to every 3 oxygen atoms. Iron is Fe, and to indicate 2, subscript of 2, and oxygen, subscript of 3. It's important that these be subscripts, not superscripts. Superscripts are used for charges. They have to come after, not before. We're trying to make it concise so that we don't have to write a whole bunch of junk. But in order for this to be understandable, we all have to follow the same rules. Okay? Any questions? You'll notice in these examples, the metal goes first and then the non-metal, or the one that's closer to the metals and the one that's further away. Some formulas contain groups of atoms that act like a unit. These are called polyatomic ions if they have a charge. So here's an example of a compound like that. So Mg, and then this NO3 acts as a unit. And so instead of multiplying this through and saying N2O6, we keep it NO3 and we put it in parentheses and we put the number of those groups on the outside. This is a little like shopping at Costco. You want a bottle of ketchup. You can't buy 1 bottle of ketchup at Costco. You can buy 2 giant bottles of ketchup bundled together, or you can buy a small bottle of ketchup, small-ish, Costco sizes, ketchup, mustard, and mayonnaise shrink wrapped together, right? You can't just buy 1. So I think of this NO3 as being a little bit like one of those bundle packs at Costco. And the parentheses are the shrink wrap, and outside the shrink wrap, I'm going to indicate how many of those packages do I have. So if I have 2 of these packages, then in this formula, there are 2 nitrogen atoms and 6 oxygen atoms. You see that? But instead of writing it individually, which would be Mg N2O6, we group them together because a chemist recognizes NO3 as the nitrate ion. And by the end of the semester, end of this 4-week session, you'll recognize it as the nitrate ion also. And so we see this and we kind of like, I'm not sure exactly what that is. So this is what it means, but that's not how we write it. So the parentheses around a group. Any questions about that? So looking at chemical formulas, we should be able to figure out how many atoms of each element are present in here. So there's 3 elements here. And you can tell that because there's 3 capital letters. Every element is going to have 1 capital letter. If there are lowercase letters, that's just part of the same symbol. So 3 capital letters means there's 3 elements. There's potassium and sulfur and oxygen. How many potassium atoms? 2. How many sulfur atoms? 1. And how many oxygens? 4. That's not so bad. Here, Al, S, O. So this is 1 element, 1 capital letter, S, another one, and O. So here we have Al, aluminum, S, and O. So how many aluminum atoms? 2. How many sulfur atoms? 3. Because here we're purchasing a bundle pack at Costco that has 1 sulfur and 4 oxygens in it, and we've got 3 packages. So we have 3 sulfur atoms, and how many oxygen atoms? 12. Okay? Yes?
So when you would write that, it would be Al3SO12?
Well, if I was writing out the answer to this, or writing the formula?
Just writing out the answer.
Writing out the answer, like on Mastering Chemistry, it might be Al2, S, 2, comma, O, I'm sorry, not 2, the 3. And oxygen is 12. There's not really a standard notation for how this question would be answered. I don't know if that helps. But this is how the formula, the chemical formula, would be written. What we need to do, not to find some particular format here, we need to be able to look at this and identify how many atoms so that we can calculate a mass. Yeah?
I think what I mean is, on the previous study you mentioned, you don't put it on both the S and the O. On the previous study I mentioned,
Yeah, so we would not write it like this. We wouldn't do that. We wouldn't do this. This one is the correct number of atoms of each element, but because this is a group that stays together, we put parentheses around it. At this point, because we haven't talked about what those groups are, it kind of seems maybe a little arbitrary and random, but hopefully it'll make sense later. So this one would just be wrong in any sense, and this is the, that's like a dollar biller thing. I know what you mean, but it's weird. So those are chemical formulas. There are different types of chemical formulas. Empirical formulas, molecular formulas, and structural formulas. So an empirical formula is going to give us the relative numbers of atoms of each element. The molecular formula is going to tell us how many atoms are actually in a molecule of that compound. So the empirical formula and the molecular formula may be the same, but they might be different. And then a structural formula is more of a drawing. It shows us how those atoms are connected, so it gives us more information. We can also have models, and we've seen some models as illustrations. This is our attempt to give us a visualization of what these molecules look like. So a ball and stick model represents the atoms as balls and the chemical bonds, the things that hold them together, as sticks. So they're a little like scientific tinker toys. Space-filling models are what we've mostly seen in the illustrations in the textbook so far. And here we're showing the atoms as sort of overlapping spheres, and this gives us a closer idea of the actual shape of the molecules. We use color. These are the colors that are commonly used for these different elements. We've seen water. We're using oxygen is red and hydrogen is white. Carbon is often indicated as black. By color coding the balls in these models, we can avoid writing down all the chemical symbols for what those things are. So it's just to help us visualize what's going on. So if we look at one particular compound, this is the name methane, and its formula is CH4. So here's the molecular formula. This tells us that there's one carbon atom and 4 hydrogen atoms in a molecule. For this compound, the empirical formula, the ratio, is the same. 1 to 4 cannot be made any more simple. So 1 to 4. The structural formula tells us how those are connected. The carbon atom is in the center, and each hydrogen is bonded to a carbon atom. In actuality, that's the only way 4 hydrogens and 1 carbon can be put together. But if you don't understand how things bond, you could draw all kinds of crazy things. You could, well, why not that? Well, there's lots of good reasons why it's not that, but from this, if you don't know much chemistry, you could stick them together any way you want. So the structural formula says, no, this is the right answer, not that one. That one's crazy. So this tells us how they're connected. The ball and the stick model gives us an idea of how they're arranged in 3-dimensional space. It turns out, the carbon's in the middle, But it's not a flat molecule like this. It looks, it's actually three-dimensional. It's got this funky tetrahedral shape. Are there big gaps between the hydrogen and the carbon atoms? No. It's actually more of, this is a space-filling model. This is more like what a methane molecule looks like. When you get into larger molecules, though, with the space filling, it can be hard to see what's what, because it kind of obscures what's on the other side. And so the ball and stick model is more open, and so it's easier to see what's going on. So all of these have their uses. The reason we have different ways of representing them is because the different methods are useful in different situations. So images help us to visualize. Like I mentioned, I'm a visual person. I need to be able to see it, at least in my imagination, or I can't even. You know, some of you have unusual names. They're beautiful. But if I don't see your name on the roster and I hear a name that I've never heard before, if I can't imagine how to spell it, I can't even repeat it back to you. It's the weirdest thing. Once I see how it's spelled, I might not pronounce it correctly, but I can recognize it then. So it's funny how that is. Not everyone's like that. But I am visual, and so I will be trying to give you a lot of visual stuff for some of this really abstract business called chemistry. So there are different levels at which we can look at the world. A macroscopic level is at a level of we can see it with our eyes. I can see my cup and the meter stick and the mouse. I can see you sitting there. I can see these crazy animal heads on the walls. They're still staring at me. We can imagine zooming in to the atomic and molecular world where we can see, in our minds at least, the individual particles. So this is a molecular picture of what's going on. The macroscopic, you look at a cup of water and you see this clear liquid. What's going on inside, though, is this molecular level. We can't actually see this, even with powerful microscopes, but we can draw pictures of it, and then we can see the pictures in our mind, and that helps us to understand how the matter behaves. And then there's the symbolic way of visualizing things, and so that's writing this symbol, H2O, to represent this molecule. When I have this picture firmly in my mind, H2O brings up that picture of these little Mickey Mouse head water molecules.